Hello, I am Ahmed Zulmez. Welcome to the final presentation of Team 29 Smart Solar Panel Project. Our primary goal was to design a portable smartphone controlled and highly efficient solar tracker. While I handled the project management and legal processes, Ali developed the system concept, Berkay completed the hardware prototyping, and Levent designed a Bluetooth software architecture. Our research shows that fixed panels lose 30% of potential energy. Unlike bulky and expensive market alternatives, we engineered a highly portable solution. We solved inefficiency of static panels with a high precision, lightweight, and low power prototype that is fully controlled by a mobile app. On the engineering side, we achieved a tracking deviation of under 5 degrees, integrated IP65 outdoor protection, and kept the total budget under $120. In our objective tour, we assigned the highest weight to smart control logic and tracking precision, followed closely by low cost and portability. Regarding legal and safety standards, we ensured user safety through electrical isolation, CE compliant, and data transmission and strict environmental protection criteria. Ultimately, our project successfully met all the constraints. Now I will pass the floor to my team for the technical details. Thanks for listening.
Hello, my name is Levent Yenger and I'm the software engineer for this project. Today I will briefly discuss what we've done in the software domain for this project. First, we determined what our software requirements were for this project. We discussed how the project should be structured from the algorithm to be used to ensure maximum efficiency to the user-friendly interface and even which communication network to choose. Later, when we started the project, we decided to use C++ as the programming language and Bluetooth as our communication network. The reason for this was to ensure our microcontrollers could achieve the fastest response times while keeping power consumption to a minimum and optimal for a direct communication channel that doesn't require any internet communication. During the development process, when we implemented these decisions, we conducted unit and integration tests. These tests verified whether the data from the light sensors was being correctly processed by algorithm and whether the Bluetooth connection was synchronized with the indicators on our mobile app. We also considered how the system would handle potential issues. Even if the connection is lost, the sensors and microcontrollers will continue to operate autonomously. Finally, I can say the real-time indicator we designed for our software gives us a competitive edge in the market for our low-cost project. Thank you for listening.
Hello everyone, my name is Berkay Temez and I'm the hardware engineer of this project. First level 0 design of our system, which is black box model. Our system takes solar radiation and smartphone control signals as inputs. The internal mechanism uses real-time light data to autonomously orient the panel towards the sun, achieving a 90% peak alignment efficiency. Consequently, the system provides a regulated 50-watt DC power supply, real-time status, and alignment data that can be monitored through the mobile app as output. As shown in Level 1 block diagram below, our system operates through a clear workflow. The power management unit stabilizes energy from the 50-watt solar panel to save the powered electronics. Meanwhile, a sensing array feeds the ambient light data to the microcontroller, which drives the dual-axis actuators to keep the panel perfectly aligned with the sun. Finally, a wireless module links to the hardware to a smartphone app for real-time monitoring and remote control. In our Level 2 hardware design, the power management unit divides 50-watt panel power into a 3.3-volt logic supply, motor power, and battery charging. Simultaneously, the sensing array converts solar radiation into 0 to 3.3-volt analog signals. The microcontroller uses this data to pinpoint the sun's position, actuating the X and Y axis motors to achieve our 90% alignment target. And also it manages two-way Bluetooth communication with the app to exchange real-time power, battery and temperature telemetry as well as manual commands with the smartphone app. And finally, we test individual parts like sensors, motors, and wireless modules, as well as the complete system. Two major steps in this plan are the tracking algorithm accuracy test, which checks if the panel moves correctly to its or 90% solar alignment goal, and the maximum power output test, which confirms the panel truly delivers its full 50-watt capacity under direct sunlight.
Hello everyone, my name is Ali Tunç. I am the system engineer of the project. To meet our 50 watt target, we evaluate alternative architectures using a weight decision matrix. The combination of a dual-axis tracker, ESP32, and MPPT algorithm achieved the highest score. Although the dual-axis mechanism adds the weight and cost, our trade-off analysis proved it it is strictly necessary to consistently reach our 50 watt peak power goal. Next, our UML use case diagram defines the system boundary and user interaction. It illustrates how the operator can easily perform OTA firmware updates, manually override actuators, and monitor live telemetry. Our project timeline is mapped on this Gantt chart. For risk management, we prioritize potential failures by impact and likelihood. For example, to mitigate battery overrating, our plan A ensures proper ventilation, while our plan B uses an NTC thermistors to safely cut off charging process. Finally, you can see our fixed and variable expenses in the cost analysis table. Based on these figures, our graphs show the breaking point is exactly 40 units. Every sale beyond this puts the project directly into profitability. Thank you for listening.